I think we should just get going. So let me introduce today's speaker. So I know Irati obviously from her excellent work in quantum optics, but I also know her from like a personal experience where both of us managed to get stuck in Rome airport because some gentleman outside Rome airport had decided to burn some tires and accidentally cut the main electricity wire going into the airport, and we were both going to a conference in Brazil, so it was like a very fortunate way that we got a few hours to spend at Rome airport and talk about quantum physics, and that's a great memory that I share with Irati. So Irati is an experimental physicist at the Quantum Information Science and Quantum Computation Group at the University of Vienna. She graduated from her PhD this summer with a thesis entitled Graphene Nonlinearities for Quantum Computing under the supervision of Philip Walter. And she's now a postdoctoral researcher at the University of Vienna in the same group as she did her PhD. So with that, I'm gonna hand over the virtual floor to you, Irati, and yeah, just feel free to take it away.
Okay, so thank you for the kind introduction, David. I'll try to be loud. If you don't hear me, just tell me something.
I think this is good.
Okay, maybe I lose my voice halfway, but I'll do my best. So yeah, as David said, I have been working with photonic quantum computation, and today I brought you a little kind of like a side project from my main thesis that I find very cute, and it's a little bit theoretical, but it's also like a very nice way of seeing like how like quantum computing could be universal and scalable in the not so long term. So just to give you a little brief introduction, in the group of Philip Walter, we are working in general with photonic quantum computation. And at the moment, there are two main drawbacks that this field is facing. The first one is that the single photon sources that we have are non-deterministic, which means that we cannot press a button and have single photons every time we want. And the second drawback is that the quantum logic gates that we use have low fidelity, which means that in our case, they are probabilistic, right? So that means that we cannot really like have a lot of gates one after the other, because then because of the probability, we would end up with a very inefficient system. So it sounds like we are very far from attaining this like universal and scalable photonic quantum computer, but the truth is that we could overcome all these issues if we would find very strong nonlinearities. At the moment in nature, if we look for very strong nonlinearities, those would be found in single atoms. But the problem is that in order to work with single atoms, we require like ultra high vacuum, cryogenics, laser cooling, etc. And that's kind of like hindering the scalability of these systems, right? Because if every single gate would require a huge system around it, then we would need a full building just to process a couple of bits, right? So that wouldn't be like really feasible. So let me introduce you our solution to this. Because I don't really know the background of the people, I'm gonna start by explaining the very simple basis. So let me introduce you the swap logic gate. And in this case, I'm actually basically making the swap gate by a directional coupler. So in a directional coupler, we have two fibers that are placed so close to each other that the evanescent field of the photon allows us to go from one to the other one. So there is certain interaction length after which we can know that if we input one photon on the upper fiber, it will always end up on the lower one. And this is exactly the swap logic gate. So now what happens if we shorten this interaction time to half of that? So now we can no longer know whether the photon has actually swapped modes or not. And because of that, we will have a superposition of states. And this is the so-called square root of swap, which together with single qubit gates, it's a universal quantum gate, which means that with this and single qubit gates, you can have any any kind of computation. Okay, so now we go a step farther and imagine that we not only have one photon, but two of them. which means that we have a photon in the upper mode and a photon in the lower mode. And once again, we have this half interaction length that is basically creating some sort of uncertainty. So because this is a probabilistic process, we know that 50% of the times we are going to find photons on the different output ports. And in this case, we are actually going to have a beautiful entangled state. But again, because it's a probabilistic process, we know that the other 50% of the times, the photons are going to be bunched in the same output port, either in the upper one or the lower one. And not only, but mathematically, it looks way more boring, but also there's nothing we can do with this state. So basically what I'm trying to say is that 50% of the times we would have a success gate, and then 50% of the times this will just fail. And this is actually for the case where we have distinguishable photons, right? Because when we have indistinguishable photons, because of the Hongo-Mandel effect, 100% of the times the photons are gonna bunch with each other, and that means that the gate will always fail. Okay, so basically we're saying we may have a universal quantum gate, but it doesn't really work because it's like completely probabilistic even when you have like distinguishable photons, and it's definitely not scalable. So we had to look for solutions. So the first one is post-selection. Post-selection has been always used and it's still being used. Basically, it means that I look at the output, I see what the output is. If I like it, I keep it for my statistics. If I don't like it, I just discard it. So it's definitely a method that works, but it's a method that is not scalable because we have huge losses, right? So it's, for us, it's just like no solution. Good. So this is where the famous Zeno effect comes in play. And this is like the basis of our work. So the Zeno effect has been a little bit fashionable now lately. It's kind of like a good password to use, but it is also true that it's kind of like a magic effect. And I had some troubles really understanding what it is about. So I'm gonna take a little bit of time to explain you what this is about, or like the two main interpretations that really help me understand it. So the first interpretation is based on the following claim that says that continuous observation of the system keeps the system in place. So let me just show you a little example. Imagine we have a two-level system where we have a ground state and the excited state. And now we're going to set the initial state to be in the excited state. So you may agree, better or worse, that on the shape of this line, but we know that eventually it's just going to decay onto the ground level. But if we make a measurement in a very early time, there is a very high probability of finding the system in the excited state. So if this happens, we are actually going to collapse the system back into the excited state, and it would in principle evolve, but if we make another measurement, we can collapse it again. And if we do this once and again, the only thing I'm saying is that by observation, I'm keeping the system in place. Good, so this was kind of like the quantum interpretation, but there is even a classical one where the Zeno effect also like plays a very strong role. And the following says that the system always avoids a lost channel. Okay, let's see how this works. Imagine we have a linearly polarized light, and in this case, we have it polarized in the vertical direction. And now we have a horizontal polarizer. Within some experimental errors, we know that there is pretty much no light that is going to make it through. But what happens if instead of having the polarizer completely in the horizontal, we have it slightly off from the vertical? So then we know that there is some light, which is actually this projection, that is going to make it through. So it's definitely something more than zero. And we can do that again. And if we do it in a repeated mode, then we end up having some light that is by far not zero. And actually, if we go to the extreme, in the case where we have a continuous change of the polarization, or which would be the same as saying having an infinite amount of steps between the vertical and the horizontal, then all the light would make it through. And it's like a very simple calculation, right? Okay, so let me remind you that I was talking to you about this square root of swap gate, where we want to get rid of those cases where two photons are found in the same waveguide. So in this case, the only thing I'm saying is that the Zeno effect would be very helpful because if we would have a two-photon absorber, the system would never evolve into these cases that we want to get rid of. So actually, it's not like post-selection because they wouldn't even be absorbed. It would just like, well, it would be evolved in a way that it never falls into those states that we don't want. Okay. I have to say that this proposal was already done first by Franson and Pittman. And the thing is that they showed that this works, but they were using atom clouds to perform as like to be the two photon absorber. And this is kind of like the drawback in our case, right? Because once again, we're talking about atom clouds, which are difficult to handle, that require a lot of engineering techniques. And because of that, we don't really see this as a scalable gate, and that's why we sort of like got the idea and thought, okay, how can we apply a strong two photon absorption with our system, right? And in our case, we are using graphene. So let me introduce you to our graphene gate, right? So here you can see that instead of having, well, it's basically a directional coupler, but instead of having waveguides, we have graphene nanoribbons. And then instead of having photons, we have plasmons. So basically the physics is pretty similar. It's just different, right? It's either electromagnetic wave or you just have like some electrons dancing around. So here there are some parameters that we can play with. The first one is the width of the nanoribbon and also the energy of the nanoribbon, so the Fermi energy. So basically with this, we are sort of tuning the resonance of the plasmon that we are exciting. And on top of that, we can also have some control over the interaction length to make sure that we have this square root of swap and also this coupling distance in between. But here for simplicity, we're just gonna keep it constant. I think it was something around like 3 nanometers or something like that. So again, the concept is pretty much the same. We input one plasmon on the upper mode, we input one plasmon on the lower mode, and then in the output ports, if they are bunched, we are gonna consider that to be a failure. And these are what I'm gonna call like this like homomandal states. And then if they output in different output ports, then we will end up with this beautiful entangled state. So how do we do this mathematically? So we have a very simple description where we describe the gate as a 6-state system. And then there are 3 parameters that are important. One is the coupling between the nanoribbons. So this is the one that is gonna allow us or allow the plasmon to jump from one nanoribbon to the other. And then we have 2 different decay channels. So one is the gamma 1, which is the single plasmon absorption. And we want that to be as weak as possible. So basically this gamma 1, it's related to the lifetime of the plasmon. And then gamma 2 is the two-plasmon absorption. And we want that to be as strong as possible because this is the one that is going to be driving the Zeno effect. Okay, so I said that we were talking about a 6-state system, and these are all the possible states. So here on the ground, we have the 0, 0. So these are the vacuum states where there is no plasmon on the nanoribbons. Then we have the 1 plasmon states, right? So either in the upper one or in the lower one. And then we have the 2 plasmon states. And here we have them when they are bunched, and here as well. And then in the middle, the ones that we are looking for, right? Like these are the successful one. So we want to get rid of those. And here again, you can see the different coupling or like decay channels. So here is the coupling between nanoribbons, right? Because through this interaction, we can go through these different states on the same level. And then we have the single plasmon absorption that is like decaying us from the lower states to from the upper states to the lower ones. And we have here the gamma 2. That is this like 2 plasmon absorption that is driving the Zeno effect. Okay, so again, I'm an experimentalist, so I'm not gonna really go through all the details, but it's really simple. You just have a Lindblad equation where you have some coupling coefficient here, and then you also have the decay channels, right? So at this point, I have to mention that most of the heavy mathematics was done at ICFO by the group of Javier García de Abajo, and Joel and Jose were on one hand calculating the coupling strength between the nanoribbons, and then also the gamma 2, this 2 plasmon absorption. And I just want to point out that this 2 plasmon absorption depends strongly on the 3rd order nonlinearity, or like this chi3 of graphene, and this will come afterwards a little bit. And also, I wanted to point out that gamma 1, we have set it to be 500 femtoseconds, or the inverse of that, because 500 femtoseconds is the longest plasmon lifetime that has been experimentally observed at room temperature. So this is kind of like an important factor at this point. And now let's see how we actually calculate it. So the first thing to calculate is to know what the interaction length has to be in order to have a square root of swap, because we want to make sure that we have this uncertainty and there is no anything that is unbalanced, right? So the first thing is we set our coupling coefficient, which is some sort of like Coulomb interaction between plasmons. And then we set our initial state to be the 1, 0, which means we have one plasmon in the upper mode and none on the lower mode. And then we let the system evolve and find the time at which the probability of finding the plasmon in the upper mode or in the lower mode is exactly the same. So this is going to be our square root of swap interaction time. And here in this plot, what I'm plotting is, well, my different parameters are the nanoribbon width and also the Fermi energy of the plasmons. And here you can see in the Z or in the color plot, what I'm doing is calculating what's going to be the interaction length. So in this case, because of the velocity of the plasmons, 500 femtoseconds corresponds to around like a traveling of 500 nanometers. So because of that, all the bright green areas are safe because we know that the swap interaction is going to happen before the plasmon decays, right? So these are the areas where we are safe, sort of. And then another thing is that, of course, because we change the nanoribbon width and we change the Fermi energy, the ratio between the two-plasmon absorption and the single-plasmon absorption can change. Good. So then, here in the lower plots, what I'm showing is the output probability of finding one plasmon on each of the output ports, the probability of finding the plasmons bunched on the same output port, and the probability of losing all the plasmons, so having no plasmon on the output ports. So, okay, let's see what happens. So now we are looking again at the ratio between gamma 2 and gamma 1. And in this upper right corner, in this red area, what we see is that gamma 2 is way smaller than gamma, right? It's like, I don't know, 4 or 5 or 6 orders of magnitude smaller. So basically what we are saying is that we have a system that has no strong nonlinearity. And because of that, we see that we have a very strong Hongo-Mandel effect, and the failure states are very, very high. Good, so then, if we go more in this direction, so basically a smaller nanoribbon width and a little bit smaller Fermi energies, we see that gamma 2 and gamma 1 are starting to be a little bit comparable, which means that basically we have a stronger loss channel, but it is still not strong enough to drive a very strong Zeno effect. And because of that, you see that here, the vacuum is kind of being populated, and these are the states that are most probable to get. And finally, here in this turquoise area, we see that gamma 2 is like up to like 2 to 4 orders of magnitude stronger than gamma. And this is precisely over here where we see that the probability of finding one plasmon on each of the output ports is very high. And actually we get a success probability of 87% in this case. And this is very good. Of course, 87 is a way better than 50% and way better than 0%. But the truth is that if you would have like a very strong, like long computation, you would need a lot of gates. And that means that if you multiply this like 0.87 once and again, then you're going to end up with very low success probability. So basically, I'm trying to say that this is not scalable yet, right? So what we wanted to do is to go a little bit ahead, and because, well, we were being theoreticians and we could play a little bit around with the numbers, then we allowed ourselves to have higher quality plasmons, which means that we went all the way to 10 picosecond lifetimes. And why 10 picoseconds? Because this is the longest plasmon lifetime observed at cryogenic temperatures. So, you know, we were being theoreticians, but still a little bit reasonable. So here, once again, at 500 femtosecond, you can see that the success probability was 87%. And then you see over here that already at like 7 picoseconds, the probability is like above 99%. And so now, yes, we could be talking about like a scalable and universal quantum computing based on graphene plasmons. So this was a very, very nice result because we could show that, well, if you find a way of really like exciting these plasmons and like having a very good quality graphene, you could indeed have a very successful gate that hasn't been shown before, right? So now, because I'm an experimentalist, and I don't know, maybe in the audience there are more experimental people, I wanted to show you a little bit the work that we have been doing in the laboratory to at some point get to build these gates, right? So because of that, I would like to introduce you this latest publication that we had. So I'm sorry, it's pending, but it will come soon. So it's this giant enhancement that we have observed of the thermonic generation when we are using graphene metal ether structures. So basically, instead of having just graphene, we're trying to enhance the nonlinearity of graphene by different media. And in this case, we are using these metal ether structures. So let me introduce you a little bit our sample and our setup. So the sample is here on the left. We have a substrate that is just like some silicon and silicon oxide. And then on top of that, our collaborators at ICFO from the group of Frank Coppens, they deposit some CVD graphene. And then on top of that, we have an insulator. In our case, it's usually either aluminum oxide or boron nitride. And then on top of that, they also grow these golden nanoribbons. And the nanoribbons are basically defined or determined by the width and also the gap in between them, right? And apart from that, we also have some like drain and source paths so that we can apply a voltage. And thanks to this voltage, we are allowed to tune the Fermi energy of the plasmons. So here we have the famous Dirac cones on graphene. And basically what you can see is that if you are tuning the Fermi energy, you get to be resonant with like one photon transition, 2 or 3 photon transitions. And here on the right, I have included an SEM image just to see like the kind of quality the gold nanoribbons have. Good. So now to see a little bit, like I will show you the results of the enhancement, but like let's understand a little bit where this enhancement is coming from. So here we have a closer look of the sample. Again, we have the gold nanoribbons, the spacer, the graphene, the monolayer CVD graphene, and the substrate, right? So now what happens is that when we are shining our laser, we are actually exciting a plasmon, but in this case, it's a metallic plasmon. So now, because we have a metallic plasmon on top, but we also have it below, there is some sort of like self-interference happening over there. And because of that, we have a huge field confinement on the edges of the gold nanoribbons. And this very confined field is the one that is acting with the graphene itself. And this is where our enhancement or advantage is coming from. Good. So now a little bit even more experimental. Let me show our setup. So we have a very tunable 80 megahertz, 200 femtosecond laser system. And then the light is linearly polarized, and that is very important because after that with the half-wave plate we can tune a little bit the polarization. And I would like to point out that the enhancement only occurs when the polarization of the light is perpendicular to the direction of the nanoribbons, because this is where the confinement happens. After that we have a very tight lens and then some collimation lens, and basically what we do during the measurement is move the sample in and out of this focal point, and then we expect a signal that is like higher when the focus is tighter, right? Just because the field is stronger, or the field density is stronger. And after that, we have some bandpass filters just to filter out a little bit the palm beam from the thermonic generation that we are creating. And then we have the superconducting nanowire single photon detectors in order to detect this thermonic signal. Good. So the first step when we are doing the measurement is to make sure that the signal comes from the graphene and that we understand like the other features that may occur in this measurement, because we are using materials, different materials, and many of them also have their own nonlinearities. So we just had to like make sure that we really understand what's going on here. Okay, so here again I have the little setup, the Z direction where we scan things. Our sample, and then here we have the plot with the 4 different measurements. So in the first measurement is done just with the substrate and the spacer, and you can see here that the green line shows basically no relevant signal, which is what we would want to have. Then we also proceed and make another measurement where we have the substrate and the gold nanoribbons, and over there we also see that here the yellow signal doesn't really have any special feature. Good. And now when we move to this like red one, where we have planar graphene, we actually see that there is a nice signal or a nice feature. It's very small, but it's still very visible, especially considering that our scale is logarithmic, right? Like that's kind of important. And then finally, when we are combining our graphene together with the gold, we actually see this huge enhancement of the signal that we were looking for. And this is exactly what we would have expected. And this is what we have been observing and characterizing sort of. So the way to do that was saying, okay, what happens now? I know that what I'm doing is exciting metallic plasmons in the gold nanoribbons. So I want to know what happens if I change or vary a little bit the width of the nanoribbons. So we did that just to see if there was some sort of like resonance effect where, you know, by having the same input light, we would have different enhancements due to the different widths of the nanoribbons. And this is exactly what I'm plotting over here. So here the red spots, well, let me tell you first, this is what we call the power scaling. So basically we are changing the input power and we see how the third harmonic signal changes. Because it's a third harmonic generation, we would expect a cubic dependence. So because of that, every plot over here, it's in the log-log scale, and all the fittings have been done in a way so that the slope of the fit is set to 3, because we know we are expecting a cubic dependence. And then the only free parameter in the fitting is actually this interception point, right? So here we have measurements again of the planar graphene, and then measurements for different nanoribbon widths. And here we see that there is some sort of like resonance because, well, if you look at the colors a little bit, it looks like the wider the nanoribbons, the better the signal, until we reach 200, because then at 500 it sort of like decreases again. So we found this like a strongest signal with the nanoribbons of 200 nanometers. And with that, we could have an enhancement of the signal of like 1,500, which is like 3 orders of magnitude. And when we're talking about like nonlinear processes, this is like a huge enhancement, and this is really good, right? Because once again, if we think about like that gate that I was presenting before, this means that the Zeno effect would be stronger. And because of that, we would have like an even higher probability of getting rid of those failure cases. Good. So with this, I'm gonna close up and, well, thank all the funds and everything that have been supporting me throughout the last years, and of course Lee Rosema, with whom I have been working also from the beginning, both in the theory and in the experimental part. And now I would be very happy to answer any of your questions. Thank you.
Okay, thanks a lot, Irati. That was extremely interesting to see and hear about. So if anyone has any questions, please drop them into the Q&A section at the bottom of the screen. And meanwhile, people do that. I have a question, and this is probably, you might have kind of answered it, but and if you did, I apologize. But I'm thinking like when you are coupling, so I envision this like gate as something, because you say that the kind of coherence times was something like 500 femtoseconds or something like this. So presumably you have some qubit that you wish to couple into this system, entangle, and then couple out. So is there any work done on like kind of how this coupling would happen? How would you coherently couple a qubit into these systems, and how would you extract it? Yeah, so I guess there are two main issues. One, that when you are exciting a plasmon, it's not like a photon in the sense that you could only have a single rail encoding, because plasmons don't have polarization. They don't, you know, like they don't have any other feature. So you would have to do single rail encoding where the field itself, it's like your 0 or your 1, right? So because of that, it's not that easy to like do the transformation basically from photons to plasmons. And then the second is that also from the engineering part, exciting a single plasmon is really not easy at the moment. So there is like a huge field just like working on like having this coupling between photons and plasmons. But it is true that when we also imagine this like more big sort of like algorithm or like structure, then we would also imagine like
sort of like a hybrid where we have like photons traveling around and then coupling becoming a plasmon, making the gate, and then, you know, traveling again as a photon. But the problem is that at the moment the coupling efficiency is really, really bad. And I have to admit that in this paper we said, okay, let's imagine we already have a plasmon. But it is true that experimentally it's very challenging to actually excite this plasmon.
Yeah, I mean, that's okay. I'm a theorist. So like we always say, assume that you have like a fault tolerant quantum computer or something like this. But
Yeah.
do you have any idea of what kind of, what are the efficiencies now for these couplings? And
we're probably talking like 10 to the -8, -9, something like that. Yeah, like really bad.
Okay.
Yeah.
But when they get there, this is something they could use. I think Theodore.
I have a quick question.
Yes, please.
Who's going first? I just wanted to know how you synchronize these plasmons, because in order to do this power of swap operation, you really need them to appear at the same time and pass through at the same time.
Yeah.
And be reliable about that.
Yeah.
Was there any particular thing that you had to do to get that?
So again, because we were assuming that we just have a plasmon, we didn't really like look at that. We could probably assume that if you have like identical nanoribbons, the traveling or like the quality of the plasmon would be the same, the scattering would be the same, so then the velocity would be the same. But it is true that probably you would have to have some sort of like delay or something with which you can play a little bit with that. But I guess it would be like in any other experiment with photons, where you first sort of characterize the system, you have your delay channels, a little bit translation stages or whatever, so that you can tune that. And then once you have characterized to have it the way you want it, then you proceed to do the experiment.
Okay, thanks. A brilliant talk, by the way. I really enjoyed it.
Yeah, welcome.
I think Theodore, you had a question.
Yeah. Sorry, there was just some post arriving that was a bit distracting. Irati, very nice talk. I really enjoyed it, and I'm a little bit new to the kind of photonic space, so this was also at a suitable level for me. I work in,
awesome.
in spin quantum computing. Anyway, my question was related to the graphene, because that's something I've worked a bit with before. So when you do your experiments, and particularly for the second half, how sensitive are you to the quality of the graphene, and how do you fabricate and work with it in the device kind of manufacturing?
Yeah, the working part is really nice because graphene is very durable and very robust, so it doesn't require any vacuum, it doesn't require any cryo or anything. The way they do it at the moment is just, sorry, my boss is getting a call. The way they do it is at the moment is just CVD graphene. But it is true that they would expect to have even higher nonlinearities if they would have exfoliated graphene. The problem is that at the moment, exfoliated graphene is not easy to have like great areas, because they have around like 50 micron areas. And then the entire process becomes way more difficult, because you have to have first the flake, and then you have to also pattern the nanoribbons right on top of the flake. So everything gets a little bit more complicated, but that's definitely the next step we're looking into, yeah.
Okay, interesting. So for you, like in terms of next steps, like graphene optimization is also a significant part of the work. Yeah.
Yes, that one together also with the spacer, it's actually really important, because the plasmons that are involved in the nonlinear process are way happier when they have quality products around. So that's also the difference between the aluminum oxide, which is like a 3 nanometer and it's kind of like amorphous layer, whereas the boron nitride is really like a very nice, neat single monolayer, right? So that's another thing. You can also have some sort of like flakes and higher quality of boron nitride, and then in that case you would have to match the flake of the graphene, exfoliated graphene, together with the boron nitride, and in principle you should be getting higher nonlinear. Yeah.
Okay, and is that, how does it work then with the lattice constants of HBN and of graphene? Is it such that it works well and is good for nonlinearities, or?
I think it is good. I'm not in the fabrication process, but I don't think that it's quite a problem in the case. Yeah, I think they grow it right on top of graphene, and it doesn't seem to show any difficulty in that sense.
Okay, awesome. Thanks a lot.
You're welcome.
I have we have time for a few more questions if people have more things to ask, but I just want
quick question.
Go ahead.
It's just a very quick question. So your measure of success when you calculate your 99% or whatever your success is this the photon number or the plasmon number, or is this the full state of the qubit after an operation? So your root of swap are you just counting the number you get at the output, or is this really the full root of swap with the full state?
So in this case, what we are considering is what's the probability that I input one plasmon on each of the input ports, and they're gonna still be separated in the output port. But then again, because I said that it would be, so imagine we go back to like room temperature where we have this 87%. Then because it's single rail encoding, then you would say, like, imagine you input a 0 and a 1, for instance, then that would be no plasmon and a plasmon, in which case, unless the plasmon gets lost because of like losses, scattering, whatever, the gate will always work. And because of that, we also did process tomography, and we reached, I think for this 87%, the process tomography was above 90% actually, but just for the single reason that the 0 or the vacuum, it's always good. So it always survives. Let's put it that way. Okay. Did that answer your question?
Yeah, I guess. I just mean, so say on the Bloch sphere, I don't know if you're using a Bloch sphere or a Poincaré sphere here, but regardless, it's the same. You can end up with the right number, but not end up on exactly the right spot on the Bloch sphere because of your complex components, where you have the right, like if you take the squared, then you have the right number, but you might not be on exactly the right quantum state. And I was just wondering if you had.
You mean because of like phase shifts that you may have?
Yeah, exactly. Yeah.
Okay.
So is that something that you consider, or do you just assume that they will be good?
Exactly. So at the moment we haven't. It's definitely a big issue. Also, there are many other works where they have these nonlinearities, and then one of the issues is having the phase problems. There are some approaches, as I think England or so had some approaches to try to solve that issue. We haven't really like looked into that. We basically have a very easy model where we either have a plasmon or not have a plasmon.
Right, right. But so do you expect this to be a big problem, the phase shifts, or is this something that can be overcome?
I think it could be a killer if it's not treated well. Definitely. Yeah. Yeah.
Okay, great. Thank you. Great talk, by the way. It was very nice.
Thank you.
Yeah, it's an interesting question. Like, I think from what I understand, like IBM and Google, their biggest problem is like phase drifting now with their devices, rather than like they can do things to high fidelity, but they can't control the phase drifting. So
yeah,
yes, it's the topic of research now. I just wanted to kind of, do you know, so I mean, we've worked on the Zeno effect together, which was good fun, but like, is there any other kind of technology? You mentioned that Franzen made like a theoretical scheme of how this could work, and he talked about atom clouds. Are there like any other two-qubit operations that can be like driven by an anti-Zeno effect, or are you aware of any other technology where people work with this kind of thing, or is it the graphene specific?
So the graphene is just a platform that allows you to have a strong two-plasmon absorption, whereas it's quite transparent to single-plasmon absorption. So at the end of the day, you could play with any other material that has this property, which is not that common, right? Like at the moment we have it in atoms, and then in this case with graphene as well. So I mean, it has been done in this case with the swap gate, but I think it is because the swap gate allows you to have the nonlinearity in a continuous way. So basically, you cannot have a bulk beam splitter where you have a cloud of atoms around, because you need the process to be kind of like continuous in a certain interaction time.
Sure.
So that's kind of the limitation, and that's why I don't think there are other gates that have been like produced in this way. It's just the directional coupler is really suitable because you have a long and continuous process.
Yeah, yeah, it's really neat. I think Thierry, do you have a question?
Yes, I do have. Thanks, by the way, for the great talk. So I had a question about, I mean, you talk about graphene. Is it possible to imagine other systems? I mean, the system I have in mind is topological insulators. You can probably imagine some spin plasmon there because of spin orbit. So is it something that's it's possible to carry on those kind of similar things? I'm not talking about the difficulty in realizing that. I'm just discussing about the a potential theoretical study, at least.
Okay. I'm talking without knowing, just like, you know, my gut feeling is why not? If you have the plasmon traveling and the spin property is still reserved, like preserved, and, you know, like it doesn't decay with the scattering or anything like that, then I don't see why not. The same way you could also conserve, I don't know, like color of plasmon, like, you know, if you would have different resonances, then I don't see why, you know, that property couldn't be used as the qubit per se. But again, I really don't know the specifics because I'm really not an expert whatsoever with the spin. So I cannot tell you more than that.
Because even on the, sorry, David.
No.
Even on the graphene, so you use two nanoribbons.
Yeah.
But for example, I was thinking about a maybe more condensed. It's not necessarily easy, but it will probably need some modification in terms of realization. But for example, bilayer graphene, you already have a nice interaction between the two layers. However, you may find, you may locally use electric field. So actually you'll decouple the two, graphene layers. And so you end up with a similar system, but probably slightly more compact. I don't know how feasible it is, but is it
sure? I mean, this what we're showing is not really like how we would design it experimentally, right? I mean, the way I draw it is just to conceptually understand that, you know, the upper mode and the lower mode are first not in contact, and then they at some point come to have like interaction between both of them. But it is true that you could switch them, right? Like you could have some like voltage that works as a gate. So basically, imagine you could like have them together, apply a voltage while you don't want them to interact, and then once you apply the voltage so that they are, for instance, like in the same frequency, then have interaction. Like that would be possible, and it would definitely look more compact. But it is true that we are talking anyways about like 5 nanometer nanoribbons. So I don't really see an immediate need of like making it even more compact.
Okay, yeah, sure. Okay, thanks.
No problem.
I was also thinking this is all boson stuff you've been doing, right? Because if you would use like spin in like a 2D structure, like usually you will have some fermionic kind of stuff going on, and then you don't get the same Mundell effect. Anyway, so like, I guess they wouldn't like, yeah, if these were spin states, you wouldn't, the double occupancy would kind of be penalized by Pauli blockade maybe, or so. I guess things would be a bit different. Yeah.
But it is true that here, like even in some papers from Franson, they even talk about like the fermionization of these objects, right? Because usually you would have the Mundell effect, and that's very common on bosons, and that's kind of like what you are prohibiting, right, by applying this Zeno gate effect.
Yeah. Well, this was an amazing talk. Thank you very much again.
Very welcome.
If you wish to stay for a few moments, we're going to switch over to our standard like group meeting now. So whoever is in the group, please feel free to stay, and also you, Irati, if you want to have
sure.
a bit of a longer chat.